Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In today's episode we will discuss one very important subject, the direction of current in DC circuit. Things are no so obvious, as one might expect, and we will do a deep dive in history to find out where all this confusion comes from, and clarify what are two directions of current flow in DC circuits. So, let's begin. Again, we find ourselves in yet another electrical circuit dilemma. If you are new to electronic in general, and design and implementation of electric circuits in particular, well, here is a good one for you. There is duality in interpretation how and in which direction current flows in electric circuits. In episode 3 of this season, we gave definition of electric current and showed how electromagnetic field propagates through the conductors. If you would like to learn more about this, pause this video, and go check episode 3 of this season. In essence, the electromagnetic field propagates through the conductor, and this propagation is facilitated by electrons in outer shell of atoms of conductor. In school, we were always given a more simplified definition of electric current, as directed flow of electrons through the conductor. No matter which definition is closer to you, in essence, the natural way of current propagation in electric circuit is from negative to positive terminal of power source. If we could somehow observe with our own eyes this movement, that would be the direction of the flow of the current we would observe. So, from where does the confusion comes from? We will have to go a couple of centuries back in history to this guy, Benjamin Franklin, yes, this guy right here. In the 18th century, Franklin conducted experiments with electricity, most famously his kite experiment in 1752. He proposed that electric charge had two types, positive and negative. He arbitrarily assigned positive charge to what we now know as a deficiency of electrons, the holes, and negative charge to an excess of electrons. He also assumed that electricity, or electric fluid, as it was called then, flowed from positive to negative. Based on Franklin's convention, scientists adopted the idea that electric current flows from positive to negative. This is what we now call an engineering direction of flow of current, from positive to negative battery terminal. However, later discoveries in the 19th century revealed that electrons, which carry charge in most circuits, actually move in the opposite direction, from negative to positive. In 1897, the British physicist J.J. Thomson conducted experiments with cathode ray tubes. He demonstrated that cathode rays were composed of previously unknown negatively charged particles, which he called corpuscles, later known as electrons. Thomson is credited with identifying and characterizing the electron as a subatomic particle. This is the actual movement of electrons, which are negatively charged particles. Electrons flow from the negative terminal to the positive terminal of the battery. This is the physically accurate description of what's happening. The animation shows two currently used directions of current propagation in conduits. On the left-hand side, we have what is Benjamin Franklin's, and today's modern description of engineering direction of flow of current, as it is referred to. On the right-hand side we have natural direction, which is the real direction in which electromagnetic field propagates in conductors. Here's a key takeaway: while electron flow is the physical reality, engineering direction of current in circuits is a useful and widely accepted convention. It's widely used in circuit analysis and engineering. Since this entire season is dedicated to transistors and amplifiers, let's see where this confusion comes into play. Let's observe a symbol for NPN and PNP transistors in electric circuit shown on the screen. Three terminals are called base, collector, and emitter. When certain conditions are met, the transistor operates in one out of two distinct modes, as an amplifier, or as a switch. Difference in marking of arrow denotes which transistor is which. On left-hand side, we have NPN transistor, an arrow pointing downright, tells us that this is an NPN transistor. The summed current from the base and the collector terminal flows in direction in which arrow is pointing. We know that this is called an engineering direction of flow of current in electric circuits. More precisely, the arrow points the direction of current from base terminal. It is said that current flows from base terminal. On the right-hand side we have a PNP transistor, an arrow pointing down left tells us that this is a PNP transistor. Here, the collector current splits into two directions. One part will continue to flow through the emitter terminal, and a smaller part will sink through the base terminal into ground. It is now said that current flows into base terminal, as the arrow points. So, what is the big deal, you ask? Let's take an NPN transistor for example and see the natural electron flow in transistor. When NPN transistor is properly biased, a small current from base terminal will initiate proper working conditions and emitter current will start to flow. The way of electron flow is natural direction of current movement in the transistor. As you can see from animation, the electron springs from power source's negative terminal and flow through the circuit, and sink back into positive terminal of the battery. If by some fancy microscope we could observe this with our own eyes, we would see exactly this kind of movement. But this direction is in opposite to the way the arrow is pointing. The arrow on NPN transistor tells us that the current moves in opposite direction than the one in the animation. This confusion comes from electronic industry's decision that the way they will mark their components and flow of current in components and electric circuits will be engineering direction of current flow, not the natural one. Simply put, they have chosen holes, the positive carriers of current in the circuit, to be representatives of direction in which current flows. In order for this animation to be compliant with engineering framework, we would have to replace the electrons with the holes, and change the direction of movement. So, let's do that. By adopting engineering direction of current flow in circuit, and replacing electrons with holes, as current carriers, we are now in compliance with the direction at which the arrow in symbol of NPN transistor points. Now, the holes are springing from positive terminal of the batteries, and flow from the positive to the negative terminal, and sink in negative terminal of the battery. We will demonstrate this movement of the holes and electrons for PNP transistor in future video, when we dive more in workings of PNP transistors. To conclude this video, we need to address when to use engineering and when to use natural flow of electric current. First consideration to take into account is consistency. For a long time now, the engineering direction of current is a de facto industry standard, and almost every component and schematic are rendered using this direction as default. If you want your work to be acceptable and easily readable by others, you are strongly encouraged to comply with industry standards. On the other hand, if you want to describe natural physical processes, dealing with flow of electric current, then, natural direction of electrons in conduits is the way to go. By adhering to this principle, your theory, or presentation, will be in compliance with the way electrons and current are observed in nature. Can you mix these two? No. It would be very confusing, and mathematically inconsistent, to interchangeably use both directions in same. You are, of course, free to choose which one you will adopt in your projects. If you decide to deviate from standards and norms, it is prudent to note which direction of current you have chosen in your project, so that other people will have no difficulties reading and understanding your design. It is a mark of the professional. We would like to take this opportunity to say thank you to all of you who have subscribed to our channel. Special thanks go to all of you who have left comments and inquired about our videos, or just posted interesting questions of your own. Your kindness in communication and the time you have chosen to spend watching our videos is greatly appreciated. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time.